Welcome back to Physical Science 20. So we'll look at how this applies to a convex lens. So notice we drew this in the previous section in parallel, reflected as if it came from the focal point. In through the focal point, it's going to hit the focal point, but before it does, it hits the mirror, reflects out parallel. And if we extend those two lines backwards, we get the image distance, or where the image is. And you can see it's upright, the same as this, so we shouldn't get a negative answer for in terms of HI, and it's also smaller, it's on the opposite side of the mirror. So we'll look at how the signs come into play with all of that. So a convex security mirror in a warehouse has a focal length that is negative 0.5 meters. So opposite, or I could say behind mirror, I suppose. Behind mirror. 2 meter high forklift, so that's HO, the object height, and it's placed 5 meters from the mirror, so that's object distance. And of course that's positive because everything on this side is positive, everything on this side is considered negative. So image position, we're looking for DI, so 1 over F equals 1 over dou plus 1 over di. So the focal length is negative 0.5 and 1 over 5. So to isolate, so let's divide here first of all. 1 divided by negative 0.5 is negative 2.0, and 1 divided by 5 is 0.2. So to isolate di, I have to isolate 1 over di first of all. So subtract 0.2, subtract 0.2. So here I get negative 2.2 is equal to 1 over di. And of course here, multiplied side by di, divided by negative 2.2, basically gives me the same result as just simply interchanging the two. So we get that, and that's going to result in negative 0.45. So of course that negative means behind mirror. So it appears that the image is 0.45 meters behind the mirror. Another thing to point out is just be careful here. In these questions we had the same unit. The other one we had centimeters, centimeters, centimeters. This one we have meters, meters, meters. If you have a combination of centimeters and meters, you have to convert it into 1. So let's be careful with that. So that means behind mirror at negative 0.45 meters. So that's where that is. If this forklift is 2 meters in front of the mirror, the image appears to be almost half a meter behind the mirror. B, magnification. Negative di over dou. So if we take a look at that, negative di, so my di here is negative 4.5. And my object distance was 5 meters from the mirror. So we are going to get 0.090 times as large. Now, positive magnification, means image is upright. Because remember, when I got negative magnification, it means it is inverted, opposite as the object. But if I get a positive magnification, that means, oh, that's both upright. Okay? And then lastly, C here, image height. And of course, I can get it the same way I did in the previous question. HI over HO equals negative DI over dou. So object height, I was told it was 2 meters tall. This was negative 0.45. Distance of object, it was placed 5 meters in front of the mirror. So I'll multiply it side by 2, multiply it side by 2. So negative negative is 0.45 times 2 over 5. And HI gives me 0.18 meters. And then, of course, positive means upright again. So if I get a negative HI, it's inverted. If I get a positive HI, it's upright. Magnification, if it's negative, it's inverted. If it's positive, it's upright. So those are key things to know here with the signs. So the equations are set up so that those are the results that we get for those particular scenarios. Okay, so with that, mirror comparison, how do various types of mirrors compare? The table below compares the properties of single mirror systems with objects that are located on the principal axis of the mirror. Virtual images are always behind the mirror. So virtual images, those are ones that you can't pick up on a screen. You won't see them on a screen. They appear to be behind the mirror. And also what that means is that the image position is negative. So behind the mirror is considered the negative area. When the absolute value of magnification is between 0 and 1, the image is smaller. A negative magnification means the image is inverted relative to the object. Notice that the single plane mirror and convex mirror produce only virtual images. So that's interesting. A plane mirror, such as what's in your bathroom, or the convex mirror, only produces virtual image, whereas the concave, depending upon where the object is located at, it can be real or virtual. Plane mirrors give simple reflections. Convex mirrors increase the field of view, so quite often they're used as security mirrors in stores. Concave mirror, it can act as a magnifier if the object is within the focal length, because the image will appear larger. So looking at these, wherever you see an R, you could exchange that for C, the center. From the center of the mirror to the mirror is the same thing as the radius. So if you look at a plane mirror, as long as we have an object away from the mirror, its image distance appears to be behind the mirror. Magnification, it's the same size. So when you look in the mirror, you're the same size and it's virtual. Concave, there's kind of three scenarios there. Of course, there's this scenario in which we don't get an image when it's at the focal point. But if we look at when it's beyond C, the image will be in between the focal point and C. It's going to be reduced and inverted, and it's real. You can pick it up on a piece of paper. You can see it. If we're placing it in between F and C, the image will be beyond C. It'll be larger, but it's also upside down or inverted compared to the object, and also real. And if I have my object at F, I don't get an image. If it's in between the mirror, if it's in between the mirror and the focal point, my image appears to be behind the mirror, right? And it's enlarged and it's virtual. So you can look back at the previous section and you can see those examples that we did. We drew those out to get that. And we also, of course, drew the convex scenario, in which if you have your object in front of a convex mirror, it's located behind the mirror, it's smaller, and it's reduced. It's virtual. All right? So you should be able to do the assignment now. The assignment basically consists of calculations that we just did. So figuring out all these scenarios using the mirror equation and the magnification equation. All right? We'll see you again.